Hello everyone, welcome to our differential equation class. In this video we are going to talk about separable differential equations. We are going to start with a brief overview of what are differential equations, and we are going to introduce the main definitions we are going to need. Then we are going to focus on separable differential equations, and then we are going to learn how to solve them. So that's the plan for today. Let's start with a brief overview of differential equations. So what is a differential equation? Well, a first order differential equation for a function y of t is an equation of this form, where we have y prime. By the prime we mean the derivative of y with respect to the variable t. We are going to call the variable t, most of the time we are going to call it time. So this is the derivative of the function y with respect to time, equal some other function f that contains the variable t and the function y of t. So in other words, a differential equation is an equation for a function and for its derivatives, for the derivative of that function. It's an equation for y and for the derivative of y. When the equation can be written in many different ways, when the equation is written in this way, we are going to call that equation the normal form of the differential equation. What is the normal form? When we write the derivative on the left side, and on the other side we have only y, t, and we don't have y prime anymore. So we solve for y prime. Then the equation has, we say the equation has normal form. Let's see a few examples of differential equations. Here we have one differential equation, y prime minus 2y equals 0. Well, this equation is not written in normal form because it's not in the form y prime equal all the rest. But it's very easy to write it in normal form. The only thing we need to do is to move this term to the other side. And if we do that, we are going to get that y prime is equal to y. Well, this is a differential equation and is written in normal form. Another differential equation is, for example, this one, where we have the 2y we had before, and now we add a constant, plus 3, for example. This is a different differential equation from the previous one. But you see, the differential equation is an equation that contains the function and the derivative. So it could also contain the equation, the variable t explicitly. Here we were not writing the variable t inside the function, but this is the same. Let's switch colors. This is the same as writing y prime of t, because it's a function of time, equal to y of t plus 3. So on the right hand side we have y of t, but for example in this differential equation we don't have t explicitly in the equation, because this factor is a constant, this term is a constant. But in this other example we have t inside the function, of course, but now the equation contains explicitly the variable t. Another example of a differential equation a little bit more complicated is this one, where the dependence in time now is more complicated. Is sine of t multiplied by y times y prime. Is the same as this equation, but now instead of a coefficient that is a constant, we have a function of time. A more complicated equation is this one. So it is a differential equation because here we have y prime, then we have yt, y squared, yt, and t squared. So this equation is not written in normal form, but is a differential equation. So if we want, we can write it in normal form. It's very simple. The only thing we need to do is we need to move all these terms to the other side, And then after we do that, we need to divide the whole equation by this factor. If we do that, we are going to get y prime on one side. On the other side, we are going to have y squared plus dy minus t squared. So these terms with opposite sign, because they are on the other side. And then we need to divide the equation by this factor. So if we do that, we put it here, and we say this is 3t y prime. And now the equation is written in normal form. But both are essentially the same equation in the sense that both equations have the same solutions, or almost the same solution. There are some details that we are going to go over those later. Okay, a couple of remarks. The first remark is, or definitions, we are going to call the function y the dependent variable, or the unknown function. Y is also called the unknown function, because usually when you have an equation like this, you are looking for the functions y that they are solution of this equation. Not every function is such that the derivative of the function is actually this combination of the original function. This is a very specific condition for a function y. Functions that satisfy the equation, they are called the unknown function, because right now we don't know what function satisfy this equation. Usually we look for these functions. They are also called the dependent variable of the equation, and to differentiate from the other variable t is called the independent variable. Sometimes instead of t we are going to use x or any other name for the independent variable. The independent variable is the variable you are computing the derivative with respect to. So is this variable here. That's the independent variable. All the differential equations we have seen up to now, they are examples of ordinary differential equations. An ordinary differential equation is a differential equation that contains derivatives with respect to only one independent variable t, for example. So like all these examples here. There are more general differential equations that they are called partial differential equations, or PDEs. And these are differential equations for functions that depend on more than one variable, in this case time and position, and the partial derivatives with respect to both variables appears in the equation. Another definition we are going to need is the order of a differential equation. The order of the differential equation is the number of the highest derivative. For example, in all these equations we have worked here, or we have seen here, these are all these equations contain only the first derivative of the unknown function. So these are first order differential equations, and this is what we said over here. First order differential equation. The equation, this equation here, for example, is a partial differential equation that is first order in the variable t, but is second order in the variable x, because second derivatives with respect to x appear in the equation. So another definition we are going to need is what is a solution of a differential equation. Well, a solution of the differential equation is any function that satisfies the equation. For example, this function here, 3 exponential 2t, is actually a solution of this differential equation. And we can see why this is the case. So, why is that? Well, because we compute the left-hand side of the equation, then we compute the right-hand side of the equation, and then we verify that this is the same. So let's compute the left-hand side of the equation. How do we do that? Well, we have to compute f prime of t, but f prime, the derivative acts only on the exponential because 3 is a constant, we know that. So this is 3 times 2 exponential 2t, or what is the same, 6 exponential 2t. So now we compute the other side of the equation, which is 2f. And what is 2f? Is 2 times f, and f is 3 exponential 2t. And we obtain again 6 exponential 2t. So that says that f prime is actually equal to f. So f is a solution of the differential equation. So one important comment now is that differential equations, in general, differential equations may have infinitely many solutions. For example, well, let me move this a little bit here. There. So, for example, the equation we just saw, this equation here, so this equation actually has infinitely many solutions, because any function f of the form any constant k is any constant multiplied by the exponential of t, is also a solution of the differential equation. It doesn't have to be a 3 like we saw before. And we can, how we prove this statement? Well, the same way we showed that the previous function is a solution. What we do is we compute f prime. Now f prime is going to be k, and now we need to compute the derivative. So we are computing the derivative here. K is a constant, it goes outside. The derivative goes only on the exponential, drops a 2, and then we have 2 exponential 2t. And now what we need to do is to multiply by 2 f of t, and that is 2 k exponential 2t. This is f, and you see it doesn't matter what k is. For every k, we are going to have that f prime is actually equal to f. And this is for all k real. So, differential equations may have infinitely many solutions. Sometimes we are interested not in finding all solutions of a differential equation, for example, like here, all solutions for any value of the constant k, but instead we are interested in finding, for among all solutions, one particular solution that satisfies some extra condition. When the variable in the equation is time, this extra condition is usually called an initial condition, and the problem of solving not for all solutions but one specific solution of a differential equation with an initial condition, that problem is called an initial value problem. So an initial value problem, IVP for short, is to solve a differential equation of this form, y prime equal f of t and y, which, so find the solution of this equation which and the solution also satisfies an initial condition that is at some specific value of the variable t, at some specific time, the solution must have a particular value, y0. Here, t0 and y0 are given constants. So, from all the solutions of the differential equation, we are interested in finding the solution that satisfies this extra condition. So, an example of an initial value problem is solve the initial value problem given by this differential equation. Let's put it here a little bit over there. This differential equation, which is the equation we worked before, but now we have an extra condition. From all the solutions, I want the solution that satisfies at time t equals 0, takes the value 7. So, how do we solve this initial value problem? Well, solution. We have seen before, actually right here, that we have infinity many solutions to these equations, and they are of the form proportional to the exponential of 2t. So we know, let's do like this, we know that all these functions y of t, that they are proportional to the exponential of 2t with are real, are solutions. Solutions of the differential equation of y prime equal to y. So now let's find the constant k. So the initial condition fixes k, because the condition says that 7 has to be equal the value of the solution we are looking for at t equals 0. So 7 has to be the solution at 0. But we have solutions for all values of t which are proportional to exponential to t. So the only thing we need to do is put 0 in here. So exponential of 0, and if we recall, exponential of 0 is 1. So from here we get the value of the constant k. The constant k is actually 7. So the initial value problem has a unique solution, in this case, and the solution is y of t is 7 exponential to t. So this is what do we mean by an initial value problem? Finding a solution of a differential equation that satisfies an extra condition. This equation we just solved is a very particular type of differential equation. It's an example, this equation here is an example of what we call separable differential equations. So now we move on to our second half of our class, where we are going to focus on this type of equations. Separable differential equations, which are differential equations that were first introduced by Gottfried Leibniz in 1691. And we focus on these equations because these are maybe the simplest equations, differential equations that we can solve. So they are very simple to solve, and the only thing we need to do is just integrate with respect to the independent variable on both sides of the equation. So before we start talking about how we solve separable differential equations, let's introduce what is a separable differential equation. A separable differential equation is an equation that can be written in this form, where here h is a function of y, g is a function of t, which are given functions, we know them, and if you can write the differential equation in this way, we call it a separable differential equation. So let's see what this definition is telling us. This definition, so a differential equation that can be written in this way, we are introducing two important conditions when we say the equation has to be written in this form. First of all, the equation contains all the dependent variable on one side of the equation here, and all the independent variables on the other side of the equation. So here contains only y, and when we say that, we mean that there is no explicit independent variable t on the left side of the equation, and on the right side of the equation we have only time, so with the time variable, so that means there is no y on the right side. But there is a second condition, and the second condition is that on the right side here, on the left side, sorry, here, the dependence on y multiplies y prime. For example, what we are trying to say is, so let's see an example. If a differential equation of the form y squared multiplied by y prime equal, let's say, t, that is a separable differential equation because we have all the y's here, all the t's over there, and the dependence on y on the left side is multiplied by y prime. Something that is not a separable differential equation is something of the form y prime plus, so y squared, sorry, plus y prime equal t. If we change, so if we look at now at this equation, yes, this equation contains only y here, only t here, so satisfies that condition, but the dependence on y on the left side is not multiplied by y prime because this term here is not multiplied by y prime. So this, while this equation is separable, this one is not, because doesn't satisfy this second condition. Let's see a few more examples. This equation here, is it separable or not? Well, when it's written as it is right now, it's clearly not of the form of the separable equation, because on this side we should have no y, and we do have a y. So as it is right now, it's not separable, but it's very easy to transform this equation into a separable equation just by multiplying on both sides of the equation by 1 over, so both sides of the equation by 1 over 2y plus 3. See what happens. When we do that, y prime is going to be divided here by, I don't like that, it's going to be divided by 2y plus 3. And on the other side, we are going to get 1. That's perfect. Over here, we see on this side, we have no explicit variable t. And on this side, so by that we mean only y. And let's move this a little bit more to the left. And over here we have no y. So by that we mean it depends only on t. In this case, it doesn't depend on time, but the important thing is it doesn't depend on y on the right side. So now this equation is separable, and here we see that the function h of y is 1 over 2y plus 3. And the function g of t, well, it doesn't depend on t, it's just 1, which is perfectly fine. So this equation here is not written as separable, but a very simple transformation. Let's move this. Let's move that thingy a little bit more there. Now it's nicer. But a simple transformation makes the equation separable. So this equation here is separable, and people also say this equation is also separable because it's super easy to transform it into a separable equation. But one important remark is, if you integrate this equation, we cannot solve it. If you integrate this equation, we can solve it. So we like to say separable is this equation, the equation when it's written in this form. So another example is this equation here. Again, this equation is written in normal form, and it's very easy to make it separable just dividing by y. We keep the t on this side, so then we are going to have y prime over y equal sine of t. And you see here we don't have, so no explicit in this side, which is good. And then on the other side, we have no y. And this equation then is separable with the function h in the definition to be, in this case, 1 over y. And the function g, now we have a non-trivial function, is the sine of t. So we like to say, this equation now is written as separable. Some people, again, already say, this equation is separable because I can make it separable super easy. But again, if you integrate here, we cannot solve it. You integrate here, you can solve it. We are going to go over that in a minute. This equation here, very simple equation, y plus t. Well, that equation actually is not separable, and we don't know how to transform it into separable by simple algebraic manipulations. So in this case, we say the equation is not separable because we don't know how to write this equation with all the y's on one side, all the t's on the other side, as in the definition, doing simple algebraic manipulations. So these are separable equations. Next, we are going to see how we can solve these equations. So let's solve separable differential equations. We can find solutions to a separable differential equation simply by integrating on both sides of the equation. So we are going to see that in an example. Find all solutions of this equation. Notice that it's not written as separable right now. This equation is not written as separable, but it's very easy to transform it into separable equation. And then from all the solutions, find the solution with initial condition y at 0 equals 3. Okay. So if the equation is not written as separable equation, it's not written in the separable form, then integrating on both sides is not going to work. For example, here, it's not going to work to integrate on both sides. Let's see that. The equation, this equation here, is not written as separable right now. Then, if we integrate on both sides of the equation, what do we get? Well, let's integrate. So we have our equation, which is y prime of t, and is equal to t over, so it's not written as separable right now, y of t plus t squared times y of t. And what we are saying, to solve the equation, do this. Integrate on both sides with respect to, of course, the same variable t. On the left side, here, we can use the fundamental theorem of calculus that says that the integral of a derivative is the function plus a constant. So this is y of t plus 0. And what is on the other side? Well, on the other side, there's nothing we can do because we don't know how to integrate this function here because we don't know what y is. So this right-hand side is completely unknown. So the only thing we have done by integrating on both sides of the equation is we have changed a differential equation, which is here, into an integral equation because now we have y and we have the integral of y. But we did not obtain y. So integrating on both sides of a differential equation in general doesn't do anything. But if the equation is separable, if we write the equation in separable form, so how do we write the equation in separable form? Where is the equation? It's right here. Well, the first thing we can do, because we have a factor y here and a factor y, is pull it common factor. So we can write y prime. Oh, let's change colors. We can write y prime equal, and we have 2t, and now we pull common factor in the denominator, the factor y, multiply them by 1 plus t squared. This is what happens when we pull common factor y. We get the 1 plus t squared. Okay, so now that y, we can move it to the other side, and we are going to have y multiplied by y prime. That is going to be equal 2t over, and here we have 1 plus t squared. Now that equation is written as separable now, because this is our function h of y. H is just y, and this function here is g of t. G of t is all that. Well, let's put it like this. H of y equal y. Like this. There. This is g. That g is horrible, but this is g, and the other is h. So now we integrate on, so here we integrate on both sides of the equation. Okay, so now integrate what is going to happen? Well, we have our function y of t multiplied by y prime of t. Let's leave a space, and then this is equal 2t. This is our differential equation, 2t divided by 1 plus t squared. Now we integrate on both sides with respect to the same variable, which is the independent variable t. And now we can solve the equation, because what we can do here is we can, on both sides of the equation, here and also here, we can do substitution. So let's do substitution here. So what do we mean by substitution? Well, what we mean is we are going to introduce a new variable that is going to be the unknown function. The unknown function, whatever that is, I don't know what that is, but that function is going to be the new integration variable. So I'm going to call it with the same name, y. Y is going to be now y of t. Looks like what we are doing is kind of silly, but it's actually important. So let's give it a space. What we have here is a new integration variable. So now this is a variable of integration, and this here was the original function we are looking for, and then the differential of this new variable is going to be the derivative of the original of the unknown function with respect to t times the differential t. But this is exactly what we have here. This is dy. What we have just done is not something, what we did here is not something crazy, is what we always do when we do a substitution. For example, we need to do a substitution also here to do this integral. So let's do this substitution. Let's see if we can remember, we can compare with the previous substitution. So I want some space here, it's too crowded. So let's do this other substitution. Substitution. So we're going to introduce a new variable that we are going to call a variable u in this case, and u is going to be what? It's going to be this function here. In this case, I know what function is 1 plus t squared. In this case, when I do the substitution, I don't know the function, but I know whatever is the solution, that is going to be the function I'm going to change by the integration variable. Here is 1 plus t squared. This is going to be the new function, the new integration variable. And then what is going to be the du? Well, what we need to do is we need to compute 1 plus t squared derivative, isn't it, times dt, which is, well, let's write it, 1 plus t squared derivative dt, which is what we did here. We don't know what that is, but is the derivative of whatever that here is. On the variable t, we actually know what that is. It's 2t dt, and this is du, and this is exactly what I have here. So this is du. That's why here the substitution works. And that's why this substitution works here, because the equation is separable. So doing both substitutions, we end up with, on one side, we have the integral of y dy. On the other side, we have the integral of 1 over u du. Both integrals can be done in a very simple way. Here we are going to have y squared over 2 plus a constant c0, and here we are going to have the natural log of the absolute value of u plus another constant c1. I can put both constants together, so this is done, but we can write it down a little bit nicer by substitute. We need to do the substitution backwards now, so we need to put instead of u, we need to put 1 plus t squared, and instead of y, we need to put y of t. So we end up with y of t squared divided by 2, so 1/2. The two constants, I'm going to put them together, and then here natural log of 1 plus t squared plus a constant c2, which c2 is nothing more than c1 minus c0. It doesn't matter. It's a constant, an arbitrary constant. And here we have, this is the solution of the differential equation written in an algebraic equation, because we have the square, we have the divided by 2, and all that. So we call this type of solutions implicit solution, or implicit form. We can write it down in explicit form by multiplying by 2. So we are going to have y of t squared, and here we are going to have 2 natural log of 1 plus t squared, and here a c3. What is going to be c3? Obviously c3 is going to be 2c2. It doesn't matter, it's still an arbitrary constant. And then we have to compute square roots on both sides, and then y of t is going to be plus or minus, there are going to be two possibilities, the square root of 2, the natural log of 1 plus t squared, all that added to an arbitrary constant, and that is the solution of the differential equation, now written in explicit form. Also called explicit solution. That is nice. And now we have an initial condition, isn't it? Initial condition. So let's write it down like this. An initial condition, and let's put here IC, which is a shorter for initial condition. What is the initial condition, by the way? Is that 3 is equal the solution at 0. Okay. So that should fix this constant, C3. Because 3 equal the solution at 0, when the solution at 0 is plus or minus the square root of 2 natural log of 1 plus c3. So we see here that there are two possibilities, plus or minus, but the initial condition is plus, isn't it? That means that the minus solution can never be a solution, so the minus cannot be, only the plus. And notice that natural log of 1 is always 0. So from here we get that 3 is equal the square root of C3, and that means that C3 is actually 9. The initial condition fixes the constant C3, and then this is our solution. Y of t is only the positive, because the positive root, because we said the negative is not going to satisfy the initial condition, square root of 2 natural log of 1 plus t squared plus 9 square root. And this is the unique solution to the initial value problem. Didn't work very well, so let's try again. Now it's a little bit better. And that solves our example. So this is how we solve a separable differential equation. You write it as separable. So from whatever form is given, you need to write it down as separable, and then simply integrate on both sides, and on this side do the substitution that the unknown function happens to be the new integration variable. This can always be done because of the form of the separable equation, and you can solve it. So what we have done in this particular example can be done in general, and we can write this little theorem, which is the general case. Suppose we have a differential equation that is separable and is written in separable form. The y is here, the t is over there. Then all the solutions of these equations are going to be given by this formula. What is big H? Big H is an antiderivative of small h, whatever you have here. For example, in our problem, we had 1 over 8 over y. So, and we said that big H was then, no, it wasn't 1 over h, it was y, isn't it? So, yeah, it was y. So, in our case, h was y, so big H is y squared over 2, an antiderivative of small h, small y. Sorry, small h. So when the equation has this form with an arbitrary function h here, and you find an antiderivative of small h, you call it big H, and that is going to enter in the solution on the left side. On the right side is going to be the antiderivative of the whatever function you have of t on the right side. We have this weird function 2t over 1 plus t squared. Well, the antiderivative of that was the natural log of 1 plus t squared, which you compute the derivative, and obviously you get that. So that's that. And if this function happens to be invertible, you can move it to the other side, and this is the solution in explicit form. So the proof of the theorem is essentially repeat this calculation with an arbitrary function h here of y and an arbitrary function g of t, but repeat this calculation. So let's repeat it, and then we are done for today. Proof. What do we need to do to prove this theorem? Well, we have our differential equation, which is h of y of t here multiplied by y prime of t, and here we have g of t. So when the equation is given in separable form, integrate on both sides here, not in any other form, only here. And now on this side we can do the substitution. So substitution. It always works. The new variable is going to be the unknown function, so the differential y is going to be the derivative of the unknown function times dt, which is exactly what we have here. So then the only thing we need to do is to integrate the function h in the variable y, and on the other side a normal integral of the function g of t on the variable t. So we call this function big H of y plus some constant. Here, this function here, we call it big G of t plus some other constant. So then the solution is going to be h of y is going to be g of t plus some other constant c2, where c2 is the difference of the other two constants. It doesn't matter, but this is the solution in implicit form or implicit solution. So implicit form or implicit solution. And if h happens to be invertible, like it happened in our example, then y of t is nothing more than the inverse of that function on g of t plus c2. And this is the explicit solution. And that ends the proof. In our previous example, you know, in the previous example, we have y times y prime equal 2t over 1 plus t squared. So h of y is just y, which implies that big H is y squared over 2, and g of t was 2t over 1 plus t squared, which give us big G equal natural log, I'm running out of space here, natural log of, and maybe I can put a little bit more space here, yeah, and this is natural log of 1 plus t squared. And then what is h inverse of y? Well, it was the positive in this case because of the initial conditions, square root of y. So that's why with all these functions we constructed the implicit and explicit solution. And that's it. With that we finish our video today, and see you guys in the next video.